Perfect. Thanks again, and thank you for giving me the opportunity to present our work and the Cambridge Particle Meeting. It's also my first time presenting my work here, so I'm pretty excited. So today I want to present to you our work about using flame spray pyrolysis reactor as a surrogate for jet engine, or as a tool to make surrogate soot representing those emitted from jet engines. And to just give you, a small sense of how much soot is emitted every year. Every year, about 8 megatons of soot particles are emitted into the atmosphere. Now, most of it in Northern Hemisphere is coming from transportation. There's a big share coming from forest fires and also biomass burning. But what I want to focus today is emissions from jet engines. And if you look at emissions about 60 years ago, when an aircraft was taking off, this is what you could expect to see. And that, in fact, motivated the International Civil Aviation Organization to impose smoke regulations. An industry over the years has made huge progress. If you look at modern engines these days, you can barely see with black smoke coming out of these engines. And if you measure those emissions on filters, this is a picture that I got from Dr. Premlovo in NRC Canada. For modern engines, it confirms that the soot loading, emission loading from these engines have significantly decreased. Now, the fact that we don't see, or it's difficult to observe and collect emissions from these engines doesn't mean that there is no emissions. In fact, these engines make a lot of particles that are very small, and that's what it's hard to detect them. Now, emissions from modern engines have 3 main characteristics. The first one is under size. So soot particles usually emitted from turbofan engines usually have very low mobility diameters with average values less than 70 nanometers, as well as small primary particle diameters, less than 20 nanometers. The second characteristics of them is their composition. Usually, particles emitted from engines, when they're produced at thrust-producing conditions, have very high elemental carbon, and their elemental to total carbon ratio is usually higher than 80%. And the third most important parameter or characteristic of these particles or emissions is their optical properties. Because they are so rich in terms of elemental carbon, their optical properties quantified by their mass absorption cross-section is around 7.5 square meter per second, a square meter per gram. So this is the type of particles that is emitted from modern engines, and usually different soot generators are used to make surrogate soot with similar properties, so that it can be used for calibration of optical diagnostic or aerosol, other aerosol characterization instruments. One example is the well-known cast soot generator that use propane diffusion flames. Another example is the inverted burner. And you can also use a premix flame and choose conditions that result in a sooting flame. Now, what all of these soot generators share is that they use gas fuels and use laminar flames to make soot particles. And that results in the so-called temperature time histories that might be or are completely different compared to those experienced in engines. Now, if you want to compare the characteristic of surrogate soot from these soot generators with engines, let's look at how their composition, characterized by their elemental to total carbon ratio and size, mean mobility diameter compared to those emitted from engines. So here you're looking at EC to TC ratio versus mean mobility diameter for soot emitted from a jet engine. And as you can see, data is clustered around two regions, one very high in elemental carbon, and those correspond to thrust producing condition, and one with low elemental carbon. And we're mainly interested in high EC to TC ratio region because that's the standard particles that we would like to use for characterization of optical instruments. Now, if we compare same data for inverted burner, we can see that very large particles with very high elemental to total carbon ratio are produced. But when we push the particles to small diameter, their elemental content starts to go down. Same story for particles made with the cast soot generator. With particles made at different conditions or set points can be generated. But as soon as we go to small particles, their elemental content starts to drop rapidly. And the same story is true for particles made from premix flame. So just for your reference, this is the target region that we would like to make particles in. Particles with mobility diameters smaller than 70 nanometer, with elemental to total carbon ratios higher than 80%. So we thought, let's use a reactor where we can use the real fuel, the liquid fuel. And of course, flame spray pyrolysis was an ideal choice because this reactor is often used to make inorganic nanoparticles from liquid precursors. And in fact, it's usually there, you don't want to make soot particles. But then we used it, and instead of the liquid precursor, we use standard jet fuel. So jet fuel is injected from a capillary and then is atomized using dispersion oxygen. And this turbulent flame is sustained using a pilot premixed flame. So then we sampled soot particles on top of the flame. In order to avoid oxidation or stop oxidation of soot particles, we had primary nitrogen dilution. We had secondary dilution with air when the temperature of the sampled gas is low enough that oxidation doesn't happen. Then we collected particles on filters for chemical analysis, and we also sent the particles to an array of aerosol characterization. We measured size distribution of particles using an SMPS device. We also measured mass of mobility size selected particles using APM and CPMA. And we also measured the optical properties, the absorption coefficient of mobility size selected particles using packs at two different wavelengths of 532 and 807. So with this setup, we could measure chemical composition of particles, size and mass of particles, as well as the optical properties of these particles. So here you can see how the flames look like. So from left to right, we keep the amount of dispersion oxygen, the gas that is used to atomize the liquid fuel, constant at 1.25 liters per minute, but increased liquid jet fuel flow rate from 9, 10 to 12 milliliter per minute. And you can clearly see how increasing the fuel flow rate results in a larger flame and more soot emissions. This is the sampling probe that you can see in the picture, and the distance from the burner to the sampling probe is about 30 centimeters. We could also keep fuel constant and change the amount of dispersion oxygen. So by reducing dispersion oxygen from 1.25 to 1, we can get even larger flames. Or if we increase it from 1 to 2, you can see how the additional oxygen results in smaller flame and less emissions from this particle. So with changing common process parameters that are used for FSP, we can have different flames, and let's now take a look at characteristic of soot particles that we could sample from these flames. The first characteristic was the size of these soot particles, mobility diameter less than 70 and primary particle less than 20 nanometer. So here you're looking at the normalized mobility diameter of the soot particles emitted from an FSP flame using 12 milliliter per minute of liquid jet fuel and with 1.75 liter per minute of oxygen. That results in mobility diameter of 21 nanometer, very small particle. Now, by reducing the amount of dispersion oxygen by only half a liter, we could increase the average mobility diameter by a factor of 3, more than 3, to 66 nanometer. And by further decrease of that to 1 liter per minute, we could increase that to 91 nanometer. So we could control the mobility diameter of soot particles within a relatively large range. And now let's take a look at the primary particle diameter of these agglomerates. So here you're looking at the normalized primary particle size distribution of FSP-made soot particles shown in blue diamond, that for a flame that resulted in average mobility diameter of 66 nanometer. So particles sampled from that flame have average primary particle diameter of 17 nanometer, less than the 20 nanometer target that we had in mind, with geometric standard deviation of about 1.33. And this distribution is in excellent agreement from data for primary particle size distribution of particles sampled from a SAM turbofan engine at different thrust levels. So this was very promising because we had very good control over mobility diameter of the particles, and these particles resulted in these agglomerates had small primary particle diameter that we were interested in. We measured the effective density of these particles, and as you can expect, with increasing mobility diameter, the effective density of the particles decrease as they become more fluffy. And that trend agrees very well with the power laws suggested by Lobo and co-workers and Olfert and Rojak for soot particles. We also compared it with effective density of soot emitted from a turboshaft engine at two different operating conditions, one low rotational speed and another one high rotational speed, as well as soot emitted from a turbofan engine at low, medium, and high thrust levels. And the data agrees well with turbofan engine at low and medium thrust level, but the data at high thrust level start to deviate from the samples, and we think that could be due to oxidation-induced fragmentation of particles, but this needs further investigation. So with the size criteria being met, now let's take a look at the composition of these particles. And just to remind you, we were interested our particles to be in this target region, mobility diameters less than 70 nanometer and elemental to total carbon ratios higher than 80%. And all FSP-made particles, which had average mobility diameters less than 66 nanometer, had elemental content higher than 80%. It was actually close to 90%. And that's kind of expected based on the overall equivalence ratio of these flames. So here you're looking at the elemental to total carbon ratio of the particles plotted versus the global equivalence ratio of flames for soot emitted from different sources, mini-cast, inverted burner, and diffusion flame. And as you can see, when we make the overall equivalence ratio smaller, or we have leaner flames, the elemental to total carbon ratio increases. And in fact, for this FSP flame, the overall equivalence ratio is very lean because the jet entrains a lot of air, which results in overall lean combustion. And that's a further proof of why this reactor makes very graphitic particles. Now, the last criteria was the optical properties of these particles. So for that, we measured the absorption function of soot particles with packs. We also measured the number density. So we converted absorption coefficient to absorption cross-section using packs as well as CPC data. And then using mass that we had measured from CPMA and APM, we could convert that to MAC of these soot particles. So we measured particles from 75 to 175 nanometers in mobility diameter, resulting in mass from about 0.1 femtogram to 1 femtogram. And here you're looking at the data measured at 532, as well as 870 scaled to 532 with an angstrom exponent of 1. So except the very first data point with 532, the rest of the data are clustering, or the value as well as the trend agree very well with soot, with MAC of soot measured from an inverted burner in terms of value, as well as the trend that shows increasing with size of the soot agglomerate. And that agrees very well with the range of MAC values reported for soot measured with direct methods. So with that, I hope I could convince you that flame spray pyrolysis or FSP reactor can be used as a tool to make soot particles, and it gives us great control in terms of controlling the mobility as well as primary particle diameter of these particles. Soot emitted from FSP-made soot particles are very rich, at least for the conditions that we tested in terms of elemental to total carbon ratio. And they have similar optical properties as high EC to TC ratio soot that is emitted from different sources. And with that, I would like to thank you for your attention, and I would be happy to answer any questions.
Okay, thank you very much, Reza. We've got time for a couple of questions. We have 2 in already. Monson says, nice talk, Reza. What is the total particle concentration from these flames and its dynamic range?
So the total particle concentration, if I can go back here, the total particle concentration depends on the sampling system and how long our sampling probe is. So we the measurement we didn't have a very accurate estimate of the overall dilution ratio that we achieved. So I cannot comment on the exact concentrations that we have. Our overall dilution ratio was about 20 to 25. And with that, particle concentrations was in the order of 10 to the power of 7 to 8. But that needs further investigation because we did not quantify very accurately our overall dilution ratio. Okay.
Joel Corbin asked a similar question. How stable is the number of mass concentration?
It depends on the height above the burner that you're sampling, as well as the flame. So, for example, for this flame, for 10 and 20 milliliters per minute of liquid fuel, the tip of the flame was about 10 to 15 centimeter. The tip of the sampling probe was about 10 to 15 centimeter higher than the flame. And for these, we had a relatively stable size distribution. Of course, during the SMPS scan, every 5 or 6 scan, I could observe, size distributions that have not been fully captured because of the oscillation of the flame. But overall, it was relatively stable. However, if we go to larger flames, or if we put the sampling probe inside the flame, then the oscillation was more pronounced. So one way to avoid that would be to sample the particles in a tank and then take the particles from there for the characterization instrument.